Okay, so what we're going to show now is that the Carnot engine is actually the most efficient engine that we can have. So just to remind you, the efficiency of a Carnot engine is given by 1 minus TL on TH, and we define the efficiency of an engine as the absolute value of the work done divided by the absolute value of QH, which is the heat which is transferred from the hotter reservoir. Now, in order to do this, we're going to use a proof by contradiction. So in a proof by contradiction, we make an assumption, we then work through logically until we come to something which we know cannot be true. And so that shows us that the assumption that we initially made was incorrect. So in this case, we're going to make the assumption that we've built a really great engine, engine X, and the efficiency of engine X is greater than the efficiency of the equivalent Carnot engine. So we'll say that our engine X absorbs a certain amount of heat, QH prime, from the hot reservoir, and it releases a certain amount of heat, QL prime, to the cold reservoir. Now, to proceed, what we're going to do is we're going to join together our great engine X with a Carnot refrigerator. So the work coming out of our engine X is used to drive that Carnot refrigerator, and this engine and this refrigerator act between the same temperatures TH and TC. So this is shown in the schematic here. Okay, now from our assumption that our engine X had a greater efficiency than the equivalent Carnot engine, we can write that the absolute value of the work done over QH prime, the absolute value of that, is greater than the absolute value of the work done divided by the absolute value of QH. That was just from our definition of what efficiency is. So algebraically here, since the work is the same, we've got the work coming out of our engine and it's going into our refrigerator. So we can see here that QH, the absolute value, is greater than QH prime. Okay, so now we're going to consider our cycles, and from our first law of thermodynamics, we know if it goes around a cycle, the total change in internal energy is 0. So the absolute value of Q, the heat transferred, is equal to the absolute value of the work done. Now, in this case, the work done on the refrigerator is equal to the absolute value of QH minus the absolute value of QL, okay, because that's the total change in the heat and it's equal to the total work done. And this is equal, because we've got the same amount of work done in the engine and the refrigerator, to the total amount of heat transferred in the engine, which is given by the absolute value of QH prime minus the absolute value of QL prime. Okay, now algebraically, we can just rearrange this a little bit and we end up with the absolute value of QH minus the absolute value of QH prime is equal to the absolute value of QL minus the absolute value of QL prime. And looking at your figure, the figure here, we can see that that is the amount of heat which is transferred in one cycle from that lower temperature up to that higher temperature. Now, looking in externally, there's no work being done in this case because the work is being supplied by our really good engine X, and that's being used to drive this refrigerator. So all the work is being used up. So there's no external work being applied, but we are getting a heat transfer from the lower temperature reservoir up to the higher temperature reservoir. So I hope you can see the problem with this. This is a big problem because it's breaking that second law of thermodynamics, which tells us that we can never transfer heat from a lower temperature to a higher temperature reservoir without doing any work. So this tells us that our assumption must be wrong. We can't create an engine with a greater efficiency than the Carnot engine. So this Carnot efficiency, 1 minus TL on TH, is actually the greatest efficiency that any heat engine can ever have.